Hello, everyone. Mr. Minix. My name, math is my game. And today in my Algebra II A class, I don't know how long the ACT test went on for, but some people are out. So we have a couple shout outs. Shout out to Grace Mills if she's watching this back. Shout out to who else? Faith Mills. And who else? Maylee and Haley. Grace Edwards. Sydney. Elizabeth Edick. Kyle Lance. All right. And a shout out to the future Mr. Minnick for being so awesome. He always gets a shout out. So this homework, it's chapter 5, section 1, number 1. You should have said that is a cubic monomial. Cubic monomial. Number 2, you should have said it's a quadratic trinomial. So far, so good? Pretty easy stuff, I think. Number 3, in standard form, you should have put 5x squared first, then plus 7x, then plus 3. Number 4, real easy. The 9x goes first and then minus 3, so 9x minus 3 for number 4. How we doing up to this point? Good? Excellent. Excellent. Number 5, the vocabulary, it says describe the end behavior. If we look at the leading coefficient of number 5, the leading coefficient is negative. Doesn't matter that it's 2, it's negative. So on the right side of this, the graph's going to be heading down. And on the left side, if we look at the degree's 7, which is odd, and because it's odd, it's going to do the opposite thing on the end. So the end behavior is, it's up dog. Yeah, nice, good, awesome. And I think if there is one on the quiz, and you end up writing up dog, I might give you some bonus points for that. Somebody said, "Do we have to write up dog?" But you don't have to. But I think it's fun. D-A-W-G. What's up dog? Yeah, like that. Number 6, can the graph of a polynomial function be a straight line? I really hate this question. Hate's a strong word, but straight line to me is a contradiction. Because in my mathematical mind, when I hear of a line, I think of something connected by 2 points in some plane, and most planes are two-dimensional. So I think of something like that, right? And they are straight. In my applied math class today, we were talking about linear and angular velocity, though. And if you consider moving around a circle, a line on the globe is actually curved because the Earth is round, even though I think there's some credibility to the flat Earth theories that abound. So regardless, the answer to number 6, I think what they're looking for is something like yes, yes, y equals or p of x equals. You could have had anything linear, right? Like 6x minus 4. You could have had anything linear. Something constant, I would have to argue that a constant isn't necessarily a polynomial, but I did get confirmation yesterday in the pre-calculus book that you'll use next year. By definition, they define a polynomial p of x as ax to the n for all non-negative numbers n. So basically they're saying n can be any whole number, so they don't contradict themselves. Anyway, number 7, your friend claims that y equals 4x cubed plus 4 has only one turning point. That's definitely false. Describe the error your friend made and give the correct number of turning points. What do we think? Anybody have this one? There's n minus 1, so there should be how many turning points? Either 2 or 0. Because the degree is 3, there's n minus 1, so either 2 or 0. And if you wanted to confirm how many turning points there really are, yeah, the only way to do that is to graph it and look at it. Ed Bassmaster says sometimes you just got to look at it. I don't know if this is going to show up in the tape, but I'm going to try to get it to show up in the recording. So I'm going to turn up my volume here. And I guess if it comes through the speaker, you'll be able to hear it. So this might be really loud. But you guys know Ed Bassmaster, right? Might as well go for broke. I'll go for the loud graph paper too. So that might turn out in the recording. Our equation or function was y equals, what was it? Negative, or 4x cubed plus 4, right? 4x cubed plus 4. I know what a cubic function looks like. and I understand how translations work. That thing's translated up 4 units. So basically, this function, when I graph it, it's going to be centered around that point. The cubic function is going to go through the point 1, 1. This is going to go through the point 1, 4. So relative to that, I'm going over 1 and up 1, 2, 3, 4 up to here, and down to here. This function is going to look like this. Whoop. And if we look at that, are there any turning points? Does it go from increasing to decreasing? It doesn't. So that one actually has no turning points. Doing all right? Good. Okay. So moving right along then, number 8, they wanted you to put that in standard form, so it's going to be 10x plus 5, and then name it so it's a linear binomial. Good, linear binomial. Number 10, we had got 2m squared plus 7m minus 3, so that's a quadratic trinomial. Number 12, 2p squared minus p. So what's that one? Quadratic binomial, good. 14 only has one term. It's degrees 5. Anybody remember the name? Quintic, awesome, good. So it's a quintic monomial. And number 18, it's not quite in standard form, but just put the 5x squared first, then the 4x, then the plus 8. So that is a quadratic trinomial, good. I'm just going to use arrows for 20 and all those. Number 20, the end behavior there is, what do we think? Up dog. Number 22, the end behavior there, down and down. Okay, it's all good. 24, the end behavior is also up dog. 26's end behavior is Mighty Mouse, up and up. 28's end behavior is down and down. And 30's end behavior is down and up. There it is. There it is. We're rip-roaring through this. I'm going to skip over the next 3 for a minute. We'll come back to them. On the flip side of this, number 38, did anybody do the finite order differences on this where you subtract? 16 minus 7 is 9, 7 minus 2 is 5, 2 minus 1 is 1, and 1 minus 4 is negative 3. So it's not the first. If we look at the second, 9 minus 5 is 4, 1 minus 3 is 4. So it's a second, so the degree on 38 is 2. You guys do all right with that one? Cool. Number 40, I had to do that one about 5 times because I was not consistent when I subtracted. It doesn't matter if you take 10 minus 17.28 or 17.28 minus 10. It doesn't matter as long as you subtract consistently each time. You pick it up what I'm putting down? So anyway, did anybody think they figured this one out, what it was? Yeah. It was the 3rd time, yeah. And what was that difference? Did you come up with like negative 0.48 or something like that? Yeah. So this one's 3. Okay. Number 42, I would argue that number 42 is not even a polynomial. But you could say that it's constant. You could say it's a constant monomial if you really had to name it, but I would argue that it's not a polynomial. Number 46, I really hope that that when you square a binomial that you know the right way to do that. I can't wait till the lesson in chapter 5. Well, I'm going to use the entire sideboard, and we're going to use the Pascal's triangle, and we're going to expand binomials the fast way. So when you expand b minus 3 squared, you get b squared minus 6b plus 9, and we got to distribute a b through to that. So you should have b cubed minus 6b squared plus 9b. So that one is a cubic trinomial, right? Okay. 44, I think I did that one yesterday in my free time, and all my free time. It's 2a cubed minus 5a squared minus 2a plus 5. Everybody else have that? And it's a cubic polynomial. Again, if you missed that, number 44 is 2a cubed minus 5a squared minus 2a plus 5, and it's a cubic polynomial. Number 48, I love this question. This question should win the Pulitzer Prize for math questions. The graph's going up on the right, which tells me what about my leading coefficient? It's positive. Nice. Good. And then the graph has not one, but 2 turning points, which tells me that the least degree would be 3. So the least degree is 3. Number 50, write an opening question, write an equation for a polynomial function that has 3 turning points. You could have used Desmond or Desmos if you prefer. I came up with something like this. I came up with P of x equals x to the 4th minus 3x squared plus 2. And it's really cool when you look at that. When you graph something like that, it's really macadocious. Now, you're probably thinking to yourself, well, wait a minute, that's going to be really hard to graph because we got to evaluate something to the 4th power. But do you guys remember how to factor? I really hope that you remember how to factor. If you don't, you better go back and look at your notes and see how to figure out how to factor. Because if you can factor, you can graph this. What you talking about, Willis? I'll show you. If you can factor, you can graph this. I'll get out my loud graph paper again. There it is. Graph, graph, graph. So this is going to factor into what 2 binomials, anybody? X squared minus 2 and x squared minus 1. Now, this is a perfect square, or no, it's not a perfect square trinomial. It's the difference of 2 squares, right? So we're going to get 2 linear factors out of that, of x plus 1 and x minus 1, right? And in college algebra classes and in pre-calculus, they expect you to treat this as though, even though 2 is not a perfect square, they want you to factor this into x plus the square root of 2 and x minus the square root of 2. You see what I did there? So we've got 4 linear factors. If we have 4 linear factors, we know that a linear factor corresponds to what part of the graph? A linear factor is going to correspond to what part of the graph? An x-intercept, thank you, an x-intercept. So this graph then is going to have x-intercepts at the following places. This graph's going to have x-intercepts at the following places. Negative the square root of 2, positive the square root of 2, negative 1, and positive 1. You picking up what I'm putting down? This is a segue into the future. What we're going to be doing next week. Now, if you don't know the square root of 2, it's okay. It's about 1.4, okay? So this graph's going to go through right about here, boop, right about here, boop, right about here, boop, and right about here. Boop. And we know the end behavior of this graph, don't we? The end behavior of this graph is up and up. The end behavior of this graph is up and up. So on the ends, this graph's going to go whoop, whoop. And we know our y-intercept of this graph is 2. So the graph's got to go, and this is where the smart board's nice. I got this zoom feature. So I'm going to zoom in on this. We'll put that on a brand new page. I said on a brand new page. So the graph's got to be going up on the ends, and it's got to go through those points, so it's probably going to go like this. Whoop, 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 whoop. It's going to look like a W. What do you think? Maybe you found a different one. If some of you were trying these out, and some of you found something that went like this. That actually that's a turning point, right? Right here, that's a turning point, that's a turning point, that's a turning point. But some of these things kind of go like this. And they actually only have one turning point, maybe, if they kind of do something like this. Well, no, I guess, would that have one? Would that have 1 or would that have 2? Or 3, I mean. It's 1 or 3, right? You got to be careful with your turning points is all I'm saying. So I think that's almost all the exercises other than these 3 that I said we would look at in class. And we will. Number 32, the end behavior is what? Down and up. And number 34, the end behavior is down and up. And number 36, the end behavior is up dog. The number of turning points of each one of these, since they're all cubic, would be either 1, actually what, 2 or none, right? 2 or none. 2 or none. And if you wanted to legitimately find out, you'd have to graph them. And graphing polynomials sometimes is easy, sometimes it's not. 34, it was kind of like the one we saw earlier. 34 is going to be vertically stretched by a factor of 10, and it's translated up 9. 34 is going to look like this. It's going to go whoop. So that one doesn't have any turning points. 32, I couldn't graph that on my own without using a graphing calculator or making a table of values. But 36, I'm really good at factoring. What am I going to factor out of negative 4x cubed minus 5x squared? I'm going to factor an x squared out. Actually, a negative x squared, in fact. Negative x squared times 4x minus 5, right? So let's think about this. When I graph this thing, it's going to have an x-intercept at 5/4. It's going to have an x-intercept at 5/4, and it's going to have two more. Yeah. Is it plus 5? You're right. Good looking out. Thank you. Good looking out. Thank you for saving the day. That would have been disastrous. So it's going to have an x-intercept at negative 5/4, and there's two more x-intercepts it's going to have. What are they? Each factor gives us an x-intercept. That's x and x, right? Remember the zero product property? Okay, so what are the other two x-intercepts? Zero and zero. 0 and 0. What's going to happen at that x-intercept of 0 is the graph's going to actually turn around. It's going to look quadratic there. We'll talk more about that next week. What's the end behavior of 36? We said it's up dog, right? So the end behavior is up dog, so it's going to go whoop. And here it's going to go whoop. And it's going to look quadratic. It's going to look quadratic there, so it's probably going to do something like that. So that one probably is going to have the two turning points. And I know you're looking at me like I'm crazy. Maybe I am. But I know how to factor. Let's graph that on something that we can graph with. How about Desmos? DES. Desmos. It's a free graphing calculator. Negative 4x, was it cubed? And then was it minus 5x squared? Okay. How did I do with the graph? Not bad, huh? Just because I could factor. So 32, you'd actually have to graph that, like I said, or plug in a table of values. We know what its y-intercept is. We know its end behavior. So 32, we got 3 minus 1 and minus 3. So 3x cubed minus x minus 3. So that one actually has two turning points as well. So that one really has two turning points as well. As far as the increasing and decreasing intervals, from negative infinity up to that turning point, that is what we call an increasing interval. On this next segment from here to the next turning point, that's a decreasing interval. And then from here to infinity is an increasing interval. So those are the kinds of things that we're looking for on the rest of it. Does that make a little bit of sense? Any questions about the homework? Comments? Concerns? Short debates? It's been real. It's been fun. I hope it's been educational. Have a nice day.